So I'll be talking about gravitational path integral in no boundary mini superspace with fluctuation, and I have changed the title a little bit, but it will be based on this article. Pointer is one. Okay, this boundary choice in one loop complex universe. So this is the broad outline of my talk. So first I will talk some motivation and the broad picture and set up the problem. Then I'll talk about brief technical details 1, then the corresponding result that comes from it, and then second technical details and the result corresponding to that details. Then finally I'll relate the physics and the cosmology part, and I'll conclude with the outlook. Now the broad motivation is we wish to compute the path integral of de Sitter space with small fluctuation and compute the wave function on the current hypersurface, which is believed to contain some important information about the present universe, and we will stick to d equals to 4 and lambda positive throughout the slides. Now our focus will be on this metric, which is r cross s3. So this is the de Sitter metric in suitably chosen coordinates. So it has 3 variables, which is labs, nt, qt the scale factor, and hij the fluctuation. We will take rho ij to be the background metric, which is mini superspace, and S3. And the gravitational path integral we study is defined like any usual path integral summing over all geometries. And this G mu will include all matrices respecting this R cross S3 and modulo diffeomorphism. And this gravitational action we take is this usual Einstein-Hilbert plus the appropriate chosen surface terms. And these surface terms will contain one unknown function f, that is a function of 3-dimensional object which is scalar, and the curvature tensor of this hypersurface. This is a current hypersurface. Now for this metric, the path integral measure will become the product of our measure of our labs, qt, and dHij. Now since gravity is a gauge theory, we have to take appropriate gauge choice. For background, there is standard choice, which is n dot equals to 0. It means that putting labs to be constant. And for fluctuation, I will take the usual transverse stressless gauge condition. With these gauge conditions, the path integral over labs becomes just ordinary integral over n. And with appropriate host and gauge friction term, one can make this gravitational path integral well defined, like any gauge theory. Now finally, one compute this object. So I have factored this because this will not be relevant for our present talk. And this is ordinary integral over labs, and this is two path integrals over qt and hij. These are coupled at this stage. So this is the object we will be computing. To compute this, we need two pieces of information. One is for range of integration of this nc, and second is what are the boundary condition for these path integrals. Now there are two Lorentzian choices for these nc integrations. One is if nc is for real line from 0 to infinity. Since nc counts a proper time to get from one hypersurface to another, positive, by taking positive it means taking the causality into account, and it will give the notion of propagator. And if we take this whole real line, it will give the wave function, and it is solution of Wheeler-DeWitt equation. We will stick to choice 2, however one can also work in choice 1. Now we also need, apart from this choice of contour, also need the boundary condition for q and hij. And secondly, if we want to compute something beyond tree level in Einstein gravity, we should ensure that it is finite, because divergence may appear in various places. So this, after all this settled, the final object can be interpreted as transition amplitude from one S3 to another with appropriate fluctuations. So strategy will be like this: first find the boundary condition, then do the path integral over q and hij, and plus ordinary integral over labs, and then make it finite if there is any divergences. And we want to compute that which is finite. This object will be finite. Now this is the brief technical details. So we have the metric answers. We have to put in the Einstein-Hilbert plus the appropriate surface terms, and keep the terms up to quadratic in h square. So I have kept in only the bulk terms here. So this is in only the background part, and this is the coming from fluctuations. and there's a lot of surface terms that I don't write here. After we have this, we have to take the variation with respect to all of these objects, which is labs, Qt and Hij Tx, which looks like this. And by ensuring proper variation, I mean there will be absolutely nothing in this side. And then by setting this quantity to be 0, we can get Hamiltonian constant from this and the on-cell equation from this, from background Q and Hij fluctuations. And in all our calculations, we utilize only this on-cell part, don't utilize this Hamiltonian constant, and which will be related in slightly contrast with the related study where they use this Hamiltonian constant. Because if we use that, this action will look quite simple. That we don't use here, this Hamiltonian constant. Now if we do this variation, we'll find that the variation of Qt and Hij are interlinked. So if I give some boundary condition for Qt, it will automatically fixes the available boundary choices for Hij Tx. Now our choice will be where Qt describes a no boundary universe, and it is possible if we take Neumann, for example, on the Q variable. And if we do the proper variation, this is the required surface term that we need to add with the Einstein-Hilbert to ensure proper variation for fluctuation. This is equation 2, and we have infinite set of choice and labeled by this omega. For one such choice which is c equals to 0, the available choice for boundary condition for fluctuation will be like this. The infinite choice, for each of them you will have some condition on boundary of fluctuations. The simplest being Hij equals to 0. Similarly for Robin, one can figure out what are the appropriate surface terms need to add it for Einstein-Hilbert to ensure proper variation, and what are the boundary choices available for fluctuations. And all are covariant surface terms. These are all covariant because this R is 3-dimensional, H is scalar, and K is the 3-dimensional curvature tensor on the hypersurface. Now after we have figured out all the boundary conditions, we proceed to evaluate the path integral. To do this, we write Q as Q bar plus capital Q and H is Hij bar plus capital Hij. Now we have to ignore back reaction because originally we had some coupled path integral, and by ignoring back reaction it means ignoring this kind of terms from this path integral. That will involve cross term Q H bar and Q capital H. If we do that, these path integrals will be decoupled and they are connected via only labs, this NC. This one can do exactly for the boundary condition we have found previous, because those are linear boundary conditions. Now this is some scalar integral that one can do for the Neumann and Robin for background, but this is some tensor Hij. To do this, we need to do the mode decomposition over the spherical harmonics. Now this is the spherical mode, spherical harmonics on de-Sitter S3, and this is the Fourier coefficients. And then if we do this path integral over Hij will becomes the product of all Fourier coefficients this. Now if we utilize the background S3 symmetry, it means that this object is basically independent of M and N, and it only depends on L with extra degeneracy that is coming from M and N, that is this. Now we do all the path integral stuff and left with this one ordinary integral over NC, and this exponent integrand will be to the power I this curly A, and this curly A is the quantum effective action, quantum corrected Labs action, and it has some correction coming from Q bar, coming from Hij bar, some part coming from capital Q and some part coming from capital Hij, and this is the quantum corrected Labs action, and this goes like n cube for large n. So if we take this from minus infinity to plus infinity, then this is not converging, this is oscillatory integral, and Picard ellipse is a useful trick to evaluate such integral. What it does, it takes this contour and deform it to various timbals, and along each timbals one can do self-point approximation with extra factor n sigma that takes care of the orientation of the timbal. You have to sum over all the saddles here. Now if Hij is 0. This object has been computed before with exact NC integral. However, if Hij is non-zero, one can do only saddle point approximation. Now the saddles will be the full theory, will be the solution of this equation, which is the quantum character lab section and variation with respect to NC. And its solution, one can write this is the connected saddles of this quantum character lab section, and it has some background part, this correction coming from fluctuation, and this H bar part coming from the fluctuation capital Q, and this coming from capital Hij. Now these corrections to these background saddles, this basically vanish if we focus on smaller L modes and large volume. However, if we take some or all L modes that we are taking in this paper, there will always be some correction to these no boundary saddles, these corrections, and we will compute what each of these components up to leading order. Now the problem is this: in the quantum character lab section, the part coming from this Hij is divergent at the no boundary saddles, and this is the expression for no boundary saddles, and this is the Hartley-Hawking. I will stick to Hartley-Hawking because it gives the dominant contribution of the path integral. And so what we have to do, we have to extract the divergence piece from this A, and it utilizes the asymptotic forms of various hypergeometric functions, and we separate the divergence piece and the finite piece, and we remove this divergence piece by adding this counter term. And here I have used summing over all L modes by zeta function technique. This is present, this divergence is logarithmic divergence and Q0, because at Q0 is 0 at saddle points, at the saddle points. So this is a logarithmic divergence, and this is present for all L modes. This, apart from this divergence, there is another kind of divergence that will be present, that comes from summing over all L modes, that looks like this. This is the degeneracy factor, and this is log L plus A with A positive. And so we need another, similarly we extract the divergence piece and finite piece and subtract this divergence by adding another counter term to make it finite. After we do all this, we add these two counter terms and make this finite. This is the finite quantum character lab section that we will utilize in calculating the transition amplitude. Now, in calculating the transition amplitude, I will use the Picard-Lipschitz methodology that helps to pick the relevant saddles for the path integral, and they are the no boundary saddles. Now, the finite transition amplitude that we compute, this up to one loop is this. This is the critical radius 3 by lambda. If Q is greater than that value, both saddles will contribute to the path integral, and the expression looks like this. So all of these terms are finite now. This comes from Picard-Lipschitz theta sigma, and this is evaluated background no boundary saddles. This is also finite, and this is coming from Gaussian fluctuation around these saddles, and this is correction to the saddles NH for the fluctuations, and plus complex conjugate contribution. Similarly, if QF is less than 3 by lambda, there is only one saddle that will contribute to the path integral. This is again comes from this Picard-Lipschitz methodology, and if we do that, that will be the imaginary saddle. If we do that, this is the expression for this, and all of these terms again is finite in this expression, and this is the final scale factor of the universe. So this is our goal, to compute the finite transition amplitude. This is up to one loop, because we have to take correction to the saddles. This is the correction coming from fluctuations. Now the physics part is there. So this is known from long, and just summarize this literature. For background, if we expand this expression in the large volume, I will get this kind of terms. This is 6 by lambda, this is positive sign. It means that smaller lambda will be favorable, and this is the phase that grows like volume. It means that at large scale factor universe become classical in the WKB sense. And from perturbations we have this, so this is a minor sign, that means this is a Gaussian, and this L into L plus 1 L plus 2 implies that it is the scale invariant. This is L cube, and the amplitude scales as inverse of square of Hubble rate 1 by E squared, and this root over q1 that grows like scale factor, which shows the approximate classical behavior of these fluctuations on the super Hubble scale. So this is the physics part that one can dig out from these finite expressions, and that is already known from long. So thus we have recovered the standard results in inflationary cosmology, but with one difference, like here we did not assume any initial Barnes-Davis state. All we need is the correct boundary condition, which is the Hartley-Hawking no boundary in the path integral, and everything comes out of that. So this is the important, what is the correct boundary condition to the path integral. If we insert that, everything follows from that. Also it cannot explain many things, like if we take the present cosmological constant, it cannot explain the classicality properly. Also it cannot explain the inflation, correct E-flow inflations. So there are lots of problems with it. Now this is summary. So what we have done, we have treated the whole background plus fluctuations covariantly and studied the path integral. We find all the allowed boundary choices and corresponding boundary action, specifically when the background is no boundary. We found some divergences coming from this path integral Hij, capital Hij, and we remove it suitably by appropriate adding counter terms. Using Picker-Lipschitz technique, we identify the relevant saddles and compute the finite transition amplitude up to one loop. So point is, although the physics part has been long for known, so our goal was to do systematically in some mathematically rigorous way up to one loop, this computing this transition amplitude. Now the immediate future direction will be to study the other boundary conditions, because I have taken one specific choice and study the consequences of that and study the path integral of them. Another, studying the offset study of this fluctuation, because in the beginning I mentioned that I didn't include the Hamiltonian constraint. So it means it will allow us to study these gravitational fluctuations upsell and with LS case criteria, and that basically says what are the all geometries that goes into the path integral, because geometries are now complex. So what are the complex geometries that goes into the path integral is this criteria basically that one can also study, and one can also study the scalar perturbations and also do for case spacetime like for S1 cross S2 things. And this is, thank you. Yeah.
So thank you, Shubhashis, for your wonderful talk. So we can have one or two quick questions maybe.
Okay, yes. No, given Hawking for Dirichlet, right? I am talking Neumann. For Neumann,
I mean, the natural boundary condition people put is Gibbons Hawking, right? I mean,
for background. That perturbation is shown to be unstable. Means you will get plus sign here, basically.
Okay.
You will get plus sign here if you take Dirichlet basically. So Neumann and Robin are the only choice.
Okay. And you can write that in a covariant way. That's what you said. I mean, you can write it in terms of some curvature and so on.
Yes,
like Gibbons Hawking, it's written in terms of
analogous to Gibbons Hawking's terms. Yes.
You can write it. Okay. And that okay, I can talk to you later. You neglected that back reaction, but those are just cubic terms, right? I mean, at least when you wrote down those things, those are just cubic terms, right?
Yes.
Yeah, those are just cubic terms. Basically, you are truncating to quadratic in action.
Yes.
I mean, it's not back reaction. It's just you're truncating it to the quadratic fluctuations. Is that what you're doing? Like you said, Q H bar Q H bar is neglected, right?
So it means that this perturbation is affecting background basically, because.
So at one there would be like a couple terms will be there.
Okay.
On the point of fluctuation of Q and capital H. So
Okay.
those terms, those mixing terms, they basically cause a non-linearity. Right? So even if you solve the equation of motion for external objects, so
Okay.
this starts to feed in the other one. And
Oh.
that causes further complications.
I mean, capital Q is background or fluctuation? That's what maybe my confusion is just that.
So we have basically two things over here. So one, basically capital Q is the fluctuation over the Q bar, over the scale factor.
Uh-huh.
And then capital H is basically the HIJ that we introduced initially.
Oh, and H bar is the background. Oh, okay. That's my confusion. Okay. Yeah.
So hi, so thanks for the nice talk. So I have a very naive question. So can you go to the first slide? So here you are taking this HIJ.
Yes.
So is this only tensor perturbations?
Yes, only tensor perturbations. Yes.
So how do we, so we can write even del J AI plus del I AJ terms here. So how do we know that these are independent? Like the scalar perturbations that are possible in Hij, they are independent on the tensor perturbations for this metric?
So I have taken this gauge basically. So you are saying this kind of terms.
Can you switch on that?
These kind of terms you are saying.
I can't see, sorry.
What kind of terms you were saying? This
Yes.
this kind of terms.
Yes, this
But
kind of term.
we have taken this choice, gauge choice, right? These things. Transverse stressless gauge. Only the transverse modes are present here.
So you can treat them independently, these scalars and tensors for this
Yes,
metric too?
independently. Yes.
Okay. Thanks.
Independently. Yes, beyond.
So okay, maybe we can thank Shubhashis again.